SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. Today, let's take up the development of finite element equations for elements with curved edges, curved elements sometimes. So here, if you recall, at some point I told you that the finite element representation of the actual body may be correctly to that size and shape, or it might even leave out some portions. Like just recall, if you have a complex curved object, so if you have a complex geometry like this, so if you are using some simple elements like this one, triangular elements, like this. So let us look at this one. So if you are using, say, triangular elements with straight sides, so this is the element mesh, while the geometry is like this. And there are certain portions here, which I am marking as with hatched thing here. And so this portion is not being represented by the finite element mesh. So this is one error which will cause some error in our finite element computation. So if you want to avoid this one, either you use very fine mesh like here. So instead of this, so you can make the elements smaller, like you can cut it still smaller, and you can make this unrepresented portion smaller and smaller. So that's one way of reducing this unrepresented portion in the finite element analysis. And of course, we talked about some other errors, like in fact, in the last couple of lectures, we have been seeing how we can improve the accuracy of finite element calculations by increasing the order of approximation. So that's one. This is the other one. And let us see if this is the case. So how to improve this geometric error. To reduce the geometric error, what we can do is that, so instead of this, so we can use, if we can use elements with curved size. So for example, it's possible that we can have parabolic curved sides, and then the geometry also curved, and then we can almost make this as close as possible, matching with the boundary here. So this is much easier if you have a parabolic or second degree curve which can be represented easily. Then this can match with the curved side here. So if you have a second degree curved side, can match the boundary, or say curved boundary, reasonably well. in fact, it can be to any extent you want it. Okay. So here the error can be reduced very easily, very fast. So now let's look into how to develop the sides with of the element boundary. So for that, let us look at the mapping. So there is, since we have derivatives as well as integrations that need to be done, so if we cannot really do the element with curved sides by itself, okay, so we have to use some kind of mapping. Let us see if you have a, so let's spend some time with the concept of mapping. So like, see, if you have a real domain like this one, xy, and then this you want to represent using usually we like to map into a simpler domain, say xi eta, let's call xi eta a rectangular domain. So what we have here is that a point P here will be represented here by P prime by certain function here. So let us see, the mapping function can be the xi eta can be found out by some function, let us say R and S. So let us map into simpler domain. So this is regarding, of course, geometry. We will also talk about the approximations a little while later, but let's first of all look at the geometric mapping. So here, if you are given a function R and S, then you can find out, given xy, you can find out what should be xi eta. And so let us say R, in fact, if the inverse function exists, inverse mapping of the same thing, so we can say that x is equal to f xi eta f z xi eta. So this is inverse mapping. So it's very important whenever you do this kind of mappings, geometric mapping or any other function mapping here. So the mapping has to be 1 to 1. The necessary condition is the mapping has to be is to be 1 to 1. So what does this mean? So that means that every one point here will be mapped into only one point there, and also the reverse. So if you do the reverse, so every point here will come to the same single point here. So this is very important. So that means that it's also possible, for example, if you take, say, some mapping here which involves a root, square root or something like that, then if you involve a square root kind of function here, so it is possible that for every x, then there can be two xi and eta values. So it is possible that P can be multiple mapping. So the same thing is also true, that inverse mapping also may be multiple points. Okay, so this should be avoided for the mapping to be proper. Okay, so let's assume that S, it is 1 to 1 and there is no duplicacy here, in the sense that here it cannot be mapped into two domains here, or one domain cannot be mapped back into two here. So this is very, very important, because this will give rise to a lot of difficulties, inconsistencies as far as the derivatives is concerned and as far as the Jacobians are concerned. So now let's assume that it is 1 to 1. Okay, we don't have any such thing. And then let's assume that we can find the function here. But the problem here is that when you have a complex domain here, to get into a simple domain like this one, it may not be possible. I mean, you may not be able to find out this one. So for that, we can have more functions. It is not just one complex function. Instead of one complex function, we propose to use several or many simple functions with some parameters or coefficients. Let me explain this one. Okay, so what we mean by this one is that, so when you have this one as a single function, instead of that, so we can say that x can be obtained by a1 f1 zeta and like this one up to any number of parameters you want. And so similarly y can be so the advantage here is that these functions are simple, that's to start with, and also as a combination here, they can really represent very complex functions. So we would like to use some simple functions here. Okay, so here these a's are parameters are the parameters, and so that's why this is called parametric mapping. Okay, so this is why we call this as parametric mapping, is that we use some simple functions here and with some coefficients which we call as parameters. So it's a parametric mapping. Okay, so now let's specialize it for some simple functions which we know here already. Let's take some simple functions. So let us take some simple functions which we are aware are the shape functions, and let us just take again very simple shape functions, the linear shape functions here. So we have n1, for example, we have bilinear shape functions like this. Let's make use of some shape functions, simple shape functions. Okay, so if we take 4 shape functions here, so we'll have 4 parameters. So let us look at this one. So examine this one. So x is equal to a1 and 1. Shall I take n1 here? So this n1, n2, n3 are or the shape functions in terms of xi eta. And so similarly y Okay, so these are, I've written the 4 shape functions, and we know what n1, n2, n3, n4 are. So let us examine this, what kind of mappings this represents. So this is 4 nodes in xi eta. So where will it go in the xy? So this is xy is our real axis and xi eta is the natural coordinates. And so where will it go? For example, here, for example, this node 1. So where will this node 1 will go? Node 1 has -1, -1. And then if you put it in this one, what are the values of this n1, n2, n3, n4 at -1, -1? So you can, if you put it -1, -1, we already know that n1 will become 1 and n2, n3, n4, sorry, will become 0, right? So that means that the value of this x here is simply, all these things will go 0 and 1 will be 1 and the x will be 1. So node 1 here, node 1 in xi eta frame will go to where? A1, and similarly it will go to this, all these things will become 0 and this will become 1. So it will become A1, B1, right? So similarly, node 2 will go to A2, B2, and node 3 will go to A3, B3, and node 4 will go to A4. So that means that node 1 will go to A1, B1 here, right? Node 2 will go to A2, B2. This is 1, this is 2, and this is 3 here. So this is very interesting. And also you can see that as xi and eta will change, for example, along 1, 2 here, the eta is constant and xi goes from -1 to +1. So that means that if you put eta is equal to -1 and xi going from -1 to +1, eta is constant, right? And then what will happen is that x is a linear variation on xi, and similarly y is a linear variation on xi again. So that means that then xy will vary along a straight line. So it's a linear variation, x varies linearly as well as y varies linearly with xi. And if you eliminate xi, so there will be a linear relationship between x and y, which is nothing but a straight line. So like this, so it will go from here and here and here. So if you properly put these, if you properly choose these constants a1, a2, a3 and b1, b2, b3, b4, so it can represent what? A quadrilateral. Okay, so this represents a quadrilateral, and in fact, instead of writing a1, b1, a2, b3, so if you want to map onto a quadrilateral, so you can as well use x1, y1, the coordinates itself, and x4, y4 as parameters. So this is a very interesting fact here. That means that your x here will be xi, ni, I going from 1 to 4, and y also similar 1 to 4. So this is a very nice way of parametric mapping, where a simple square here in xi eta will map into the quadrilateral shape, the quadrilateral with vertices with straight sides. Okay, so this is a very interesting observation. So the same thing can also be extended. So this you can extend it to extending this concept to 8 nodes. What will you get? Okay, so in xi eta, you have 8 nodes here. 1, 2, 3, 4, 5, 6, 7, 8. And so what will you get? So X is now 8 nodes, 1 to 8. So these are the shape functions which we already have seen. Say, for example, the serendipity type of shape functions. Then you can use all those 8 shape functions here. And then what will happen here? So okay, so what do you think of this one? Again, we use the coordinates of 8 nodes here. And what is your guess here? So what will happen to the quadrilateral like this one for 4 parameter representation? Now if you have 8 nodes, so you can very well see that it will go to 8. So these 8, it will go like this one. Interestingly, so this is how the 8 nodes will be mapped. So it is 1, 2, 3, 4, 5, 6, 7, 8. So here, that means that this straight side here will become a curved side here of second degree. So that means that, so it will map onto edges, okay, of second degree. I don't say it's parabola or ellipse or hyperbola, but it's a second degree curve, which involves, so that means that x and y, they become second degree terms. And when you, so along this, for example, when you go along this one, when xi goes from -1 to +1, so the x and y will assume values as if they are a second degree curve. So so it's very nice. So that means that if you have a curved side like this one, okay, if you have any element on the edges, so like this one, so if you have some element here, so what all you need, so it is 1, 2, 3, 4, 5, 6, 7. So what all you need, so if you want to map this kind of element here with curved side, what all you need to do is that you find out what are the coordinates of this edge. So find coordinates of 1, 2, and 3 and use it in mapping. That's all. So appropriate x and y coordinates and use that here in this mapping. So Ni is the usual shape functions of 8 node serendipity, and use it here, and then you will find out what is the, you can very well represent the curved side boundary of the element. Okay, so that is the beauty of this one. Okay, so that is the one important aspect as far as the geometry is concerned. So as far as the geometry is concerned, so we can use either a simple 4-noded shape functions here to get a quadrilateral, or very simply 8-noded element is very convenient serendipity shape functions. So you can use that here and then to get a reasonably well curved side element. Okay, so this is as far as the geometry is concerned. What about the approximation here, or the variable? Of phi hat. So phi hat xy itself is now has shape functions, for example. So it has n1, phi 1, so there is something which we have to differentiate between these two. So one is the shape functions which we use in the case of geometric mapping. Here then we are using the shape functions here again for the representation of the variable, the primary variable. So these can be same or these can be different. So let us now explore this one a while. So let us see, there's a geometric representation. Geometric mapping. And the variable representation. Primary variable here, the phi approximation. So here, let us say we are using x and y. 1, 2, let us say we'll separate out these ones. Okay, so here there are two different types of shape functions which we are using. So the first Ni prime is set n prime set. So there are n prime variables which are used here for geometric representation, whereas for primary variable approximation phi hat, then we used another set of shape functions and the number is n here. Okay, so just like here, so in fact here we can use 4 nodes for representing the geometry. So if you have a quadrilateral, and then in the same quadrilateral we can have the 8 locations or 8 nodes for representing the variable phi hat. Okay, so here, so that means that n prime can be less than n, so the set is different, or n can be same as n, or n prime can be greater than n. Okay, so quickly, so if n prime is less than n, so the number of parameters are less in geometry, we call it as subparametric element, and if they are equal, it's called isoparametric element, and then this is superparametric element. So there are 3 types of elements depending upon whether n prime is less than n, or n prime is equal to n, or n prime greater than n. So these are an important classification. So I think we should look into this one a little bit more in detail, which we will do in our next class. So for the moment, it's bye.